A line in space is easily defined by simply a point and a direction. We need a little bit more information that's required to actually determine a plane. Now we can determine a plane by identifying a single point that resides on the plane and a vector n that's orthogonal to the plane. This vector n, this orthogonal vector, is said to be normal, meaning simply that it's perpendicular. Okay, let's take a look at a quick diagram here to kind of get us going. This is the x, y, and z axes, and I'm going to pick some arbitrary points here. That's simply going to help me define my plane. Okay, so here's my plane, and obviously this extends in all directions. It's not really a triangle. It's just it cuts through and intersects the z-axis, x-axis, and y-axis here. So I'm going to start off. I'm going to identify a position vector, r0. This is the position vector for the point p0. So r0, let's keep track of this stuff, is the position vector for the point p0, which is on the plane. When I say it's on the plane, I'm talking about the point p0. P0 is on the plane. R0 is not. This vector does not lie on the plane. See, it reaches from the origin out to the plane. So the tip of R0 touches the plane, and that's what identifies that point, P0. Now I'm going to take vector A and simply say that vector A is an arbitrary vector that's on the plane. And I'm going to take vector n, I'm going to add this normal vector. N is orthogonal to the plane. So this vector n, I'm saying, is orthogonal to the plane. I know it's kind of difficult to visualize that, and when it's a flat surface, we're trying to work in 3 space. Now, the way I drew this as n be orthogonal to the plane, and it's starting, its tail is at the point p0. The fact that it's at the point p0 is really not a necessary condition. I could have taken a normal vector to the plane. The tail does not have to be at this initial point. Now, n, this vector n and a are in fact orthogonal to each other. I'm going to use perpendicular. And this is going to happen if and only if a dot n, based on the definition of the dot product, is 0. Now, vector r, I'm going to add another vector here in the diagram in just a moment, is the position vector of the point P, where P is also on the plane. So I'm going to take P and put them out here. And then I have vector R. That's a position vector for P. Remember, P is on the plane. Okay, so what do I have now? I have P0, P, that vector, is a representation of r minus r naught. Now, because of that, I'm going to say so n is orthogonal to r minus r naught. Remember, r minus r naught, those are vectors. It's going to end up in another vector. So this is a vector. That would then imply then that n dot r minus r naught, there we go, must also be equal to 0 because they're orthogonal. That would then imply then that n dot r minus n dot r naught is equal to 0, which should obviously further imply that n dot r must be equal to, oops, that's supposed to be r naught right there, must be equal to n dot r naught. Now, I'm going to write vector n in component form as being equal to or having the components a, b, and c. That would then imply that n dot r minus r naught is actually going to be equal to ABC dot x minus x naught, y minus y naught, z minus z naught. Now obviously what I just did there is, whoops, I wrote that wrong. That's supposed to be a vector. I didn't write that as a vector. Now obviously the point P naught has coordinates x naught, y naught, z naught, and the point P has coordinates x, y, and z, hence my x minus x naught and so forth. Now this must be, I ran out of room here, but this also must be equal to 0. That would then imply then, if I actually multiply this out and end up with a dot product, or actually do the dot product here, I would get a times x minus x naught plus b times y minus y naught plus c times z minus z naught is also equal to 0. So I'm going to go ahead and distribute this, and what I end up getting is ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. Now remember, the point P naught is a known point. That means that these guys right here are actually constants, because x naught, y naught, z naught, and a, b, and c are all known values. Those are all constants. So what that actually gives me then is, if I collect these constants, I'll have ax plus by plus cz equals d. I'm going to say where d is the collection of all the constants. So what does that do for me? Well, this equation right here, this is the general form, which you may have seen like in pre-calculus or algebra. It's a general form of a plane in R3. So what we've done is we've taken this known point, we know this guy, and a vector that is orthogonal. So I have this orthogonal vector that's orthogonal to the plane, and then this p is an arbitrary point. So it's any x and y and z. That's why it ended up down here as x, y, and z. So based on identifying this known point with a position vector and identifying the vector that's normal to the plane, we can actually identify or work this down and actually get a or the equation for a plane. So we went from vectors down to the general form for a plane in R3. So let's go ahead and take a look at a quick example of this. I want to find the equation of the plane which contains the point P0 is 4, 0, negative 3 with a normal vector 0, 1, 2. So n is normal to the plane. So I'm going to go ahead and I'm going to let a vector r have components x, y, and z. This is going to be the position vector to the point x, y, z, which is obviously going to be on the plane. Now r0 is going to be the position vector to the point 4, 0, negative 3. Therefore, r minus r0 is going to be x minus 4, y minus 0, and z plus 3. That gives me, say, n dot r minus r0 is going to be equal to, here's my normal vector. I'm going to write like this: 0, 1, 2 dot x minus 4, y minus 0, z plus 3. And that's going to give me 0 times x minus 4 plus 1 times y minus 0 plus 2 times z plus 3. And of course, that has to be equal to 0. So this gives me y plus 2z plus 6 equals 0, which gives me y plus 2z equals negative 6. And that is actually the equation of the plane that is defined by this initial point on the plane and this vector, which is normal to the plane.